So we're going to look at cell potentials under non-standard conditions. So what we mean by cells under non-standard conditions is that their concentrations are, of the components that are reacting are not at 1 molar. So if we look at this reaction here that we've been provided with, copper is being oxidized by cerium-4 ions to cerium plus 3 ions, and this has a cell potential of 1.36 volts. Okay, so this is based off the assumption that we have 1 molar concentration of each of these ions, and those are the conditions that we're assuming. But what will the cell potential be if we change the concentration of cerium plus 4 to 1.6 molar instead? Okay, and so we can think about this problem with respect to Le Chatelier's principle. Okay, if we increase the amount of reactants, just like we see in regular chemical reactions that we've been discussing so far, typically speaking, what's going to happen is you're going to shift to the right towards your product. So increasing the concentration of that cerium-4 is going to shift the equilibrium to the right side, which will help favor products, which means there'll be more electrons being released and basically have more cell potential or a larger E value associated with this specific reaction. So let's go ahead and let's look at another couple of examples. So if we're assuming this reaction here, okay, notice aluminum is being oxidized, okay, and the manganese is being reduced, okay, and they want us to predict whether the E cell for this process is larger or smaller based on these concentrations, okay, and so once again, looking at these with respect to Le Chatelier's principle, in this situation, we are increasing the amount of our product while maintaining the concentration of our reactant. So in that type of situation, if we increase the amount of product, our equilibrium is going to shift to the left. If our equilibrium shifts to the left, that electromotive force, or those transfer of electrons that we're seeing, is going to be reduced. Okay, so under these conditions, we're going to have a smaller E cell than the E cell not that you could calculate or look up on the table based on standard conditions. Okay, in this situation, same reaction. Notice that we are increasing the quantity of reactant. Okay, we're keeping the amount of product the same, and so we're going to have a shift to the right. And if we have a shift to the right, that means that there's going to be more EMF and subsequently a larger E cell value, which is what we would anticipate. So we can look at these problems with respect to Le Chatelier's principle in a pretty generic, kind of straightforward way. Okay, now this brings us to something called a concentration cell. So far we've been looking at cells and in the context of having different components in the oxidation and reduction cell areas. Okay, so basically we'll have different types of reactants, different types of products, and subsequently different processes that are occurring inside the cell, each cell. However, a concentration cell works with the same components in each cell, and one will still be undergoing oxidation, one will still be undergoing reduction. Okay, so if we look at the examples that we provided here, what's going to happen is we're going to start with the nickel 2 plus in this cell as well as nickel 2 plus in this cell. However, the concentrations, notice, are very different. So what's going to end up happening is that electrons are going to be transferred from one cell to the other in order to basically equilibrate the quantity of nickel 2 plus that's in solution. Okay, and that's basically that driving force. That concentration differential is what's going to drive the electron transfer. Okay, so in order for these two concentrations in the two cells to basically become equal, what needs to happen is that the concentration of the nickel 2 plus ion needs to increase here and decrease here. Okay, so what needs to happen, since we have a nickel electrode, we know that the oxidation that will occur at this point will produce electrons as well as zinc 2 plus ions. So oxidation is going to occur here at the anode so that we increase the amount of zinc 2 plus ions. And reduction is going to occur over on this side because we want to take zinc 2 plus ions out of solution. So as the electrons come through into this cathode component, what's going to happen is the electrons are going to reduce down the nickel 2 plus that's floating around, and that's going to coat the electrode that's been stuck into the solution. Okay, so as this process occurs, obviously, as I said, we're going to reach a basically equilibrated concentration value, and electrons will no longer flow once that charge build up and the charge concentrations equalize. Okay, so if we want to look at another example here, they've asked us to determine the direction of electron flow and designate the anode and cathode for this cell right here. Okay, so we have an iron electrode. Okay, we have a low concentration of iron 2 plus. We have a slightly higher concentration of iron 2 plus on this side. Okay, so once again, we want these two concentrations to be the same. So what needs to happen? The amount of iron 2 plus needs to increase here. The amount of iron 2 plus needs to decrease there. So we want iron to be in the 2 plus form on this side, so oxidation needs to occur over here. Electrons are going to come over to this side, reduce down the Fe2 plus that's in solution, and you're subsequently going to see that flow from left to right as these two concentrations equalize. Okay, so this here is going to be your anode because it's where oxidation occurs. This is going to be your cathode. Okay, guys, so you want to make sure you're looking at those concentrations. You're considering what your electrode's made out of, what it's going to put into solution or take out of solution in order to decide this. Okay, it just so happens that this is written in the prototypical left to right type of setup that we've seen, but remember that could be switched at any time. Okay, so if we come back to non-standard conditions in terms of our concentration, we've discussed it so far with respect to electron flow in the concentration cells, as well as in a generic Le Chatelier type of approach. However, the Nernst equation actually allows us to have a quantitative approach to these types of problems. So basically, the Nernst equation is derived from two equations that we've already seen. We saw this in our last unit, and we saw this one here actually in our last lecture. Okay, so combining these two equations and making some additional mathematical adjustments brings us to the Nernst equation. They actually typically express it with respect to the log base 10. So as I said, there's additional math that goes on to get this. So once we know this equation, we can use it to calculate the cell potential of our specific process. Now, the N in this case is going to tell you the number of electrons that are transferred. We've been talking about N being, moles of a certain substance. In this case, in this Nernst equation, it's the amount or number of moles of electrons that have been transferred. Okay, so let's go ahead and let's apply this Nernst equation for this problem. Okay, so we've been given this reaction here. Notice we have an oxidation here, okay, and a reduction there. Okay, and we've been given concentrations. Notice these concentrations are at non-standard conditions, so we know that that Nernst equation is what we're going to be using. Now, we've also been given our E naught of our cell, which is 0.48 volts. But if we had the appendices, we could easily calculate the E naught of the cell here at standard conditions. And so that's what we've been given here. Okay, since we're using the Nernst equation, we know that we're going to need Q. Okay, and remember Q is going to be products over reactants, but we exclude any pure liquids or pure solids. So we end up with our Q value equaling the concentration of our aluminum plus 3 ion squared, because of that coefficient, divided by our manganese plus 2 ion cubed, because of that coefficient. Okay, so we can plug these numbers in that we've been given, our various concentrations, and we solve for our Q value. Okay, so the last part of the Nernst equation, obviously, is to figure out how many electrons have been transferred. Okay, so if we look at the half reactions, obviously there's been some multiplication and such to make the number of electrons transferred between the two processes be equalized, and that gives us 6 electrons in the process. So our N value for our Nernst equation is going to equal 6. Okay, so we go ahead and plug this into our Nernst equation. Okay, this is our E naught value that we were given. Okay, this is our N value right here. Okay, and obviously this is our Q value. We plug that in and we get 0.47 volts. Okay, so what ends up happening by changing these concentrations, we subsequently get a decrease in our cell voltage. So not as many electrons are flowing from the anode to the cathode. Which, if we think about it with respect to Le Chatelier's principle, works pretty well. Our aluminum plus 3 ion, we've increased that concentration. We've decreased the concentration of our manganese plus 2. Okay, so by increasing our product, we're going to shift to the left with respect to our equilibrium. So this actually makes lots of sense. So we've been told that we've been given a zinc and hydrogen cell with an E cell value, okay, of 0.45. Okay, so this is the actual voltage associated with, or the cell potential of the specific cell we're looking at. Okay, these are the concentrations of our products. Okay, and they want us to figure out the concentration of H+, which is one of the reactants. Okay, so we are going to use the Nernst equation. As I said, we've been given E. Okay, we can calculate E naught based on the reaction here from the appendices in the back of the book. Okay, N we can obviously calculate from our half reactions, and Q we're going to be solving for Q so that we can actually figure out what our H+ concentration is. So we have E. Okay, E naught is going to be calculated based on the reduction potential half reaction values from the back of the book. Okay, so we end up with reduction potential associated with hydrogen, reduction potential associated with zinc, and we subsequently get this value here. Our N value is going to equal 2. Once again, we get that from looking at our half reactions for our two processes and making sure the number of electrons given away and picked up are both the same. So N is going to equal 2. Okay, and we're going to go ahead and plug all this information that we have into our Nernst equation. So 0.45 was our actual cell potential. 0.76 was our E naught for this cell at standard conditions. Okay, 2 here is our number of moles of electrons. Okay, and so we could subsequently solve for the Q value that's here. Okay, so we're going to do some basic math to isolate our Q value, and we end up getting Q equals 10 to the 10.5. Okay, and so that equals 3 times 10 to the 10th. Now that we know our Q value, we can take this number and use the products over the reactants reaction quotient expression to solve for what we don't know. So in this case, we set up Q, we have our products, okay, divided by our reactant squared. Notice we've left out the zinc solid. We don't need that in our expression. Okay, and basically we're going to plug in our zinc 2 plus concentration. We're going to plug in the partial pressure of our H2 and basically solve this problem for H+ concentration. Okay, now some of you might be asking, why can we use pressure and concentration at the same time? In these types of problems, we're actually looking at the concentrations as activities. Kind of brings us back to some of those thermodynamic quantities. So we're actually not too worried about whether we're dealing with pressure or concentration. Okay, so remember Q is equal to 3 times 10 to the 10th. Okay, that's going to equal 1.0 times 1 ATM divided by H+ squared. Okay, so this is going to end up giving us H+ concentration being equal to 1 over 3 times 10 to the 10th to the square root. So that's going to give us a concentration value for our H+ of 6.6 times 10 to the negative 6th. Okay, and the last thing we're going to be discussing is electrolysis. Okay, so far we've been talking about galvanic cells, but now we're going to add the electrolytic cell. So let's differentiate. The galvanic cell basically produces current from a redox reaction. So we take the redox process and harness the electrical current that's being produced. So that's why we see our voltmeter. Okay, now an electrolytic cell actually produces a chemical change from the electrical energy. Okay, so basically electrolysis is going to utilize or force a current through a cell in order to produce a chemical change for a non-spontaneous process. Okay, so basically we know that going from zinc solid to zinc plus 2 in the presence of copper plus 2 ions produces a current. This is a spontaneous process. Now, to reverse this process, obviously to go back to zinc and copper plus 2 ion, basically we have to add electrical energy, and we have to do so with a power source that's greater than 1.10 volts. So electrolytic cells are basically going to produce chemical changes harnessing that electrical energy. Okay, so in that process, obviously what ends up happening is we're going to have a change in the flow of electrons and a change in what's the anode and the cathode. We're basically looking at reversing the process that we just talked about in our spontaneous galvanic cell. Okay, so a big one to look at with respect to electrolysis is electrolysis of water. Basically, we take electrical energy and we run it through water. Okay, and when we do that, what we're able to do is reverse the spontaneous formation of water from H2 and O2. And so basically we run that electrical current through the water, and it's going to split hydrogen and oxygen from the H2O molecule. So we're reversing this process. So now that we know what an electrolytic cell is, let's go ahead and utilize our understanding of the cells and stoichiometry to figure out a few things. So basically, in this problem that we're about to do, we're going to determine how much chemical change occurs based on a specific time frame. Okay, and so what we mean by chemical change in a lot of these cases is we're going from having ions in solution to having a solid plated, or maybe sometimes the opposite type of process occurring. So basically a non-spontaneous process is going to be occurring when we apply this current. So something else to review, or to look over rather, okay, so 1 amp or 1 ampere, okay, is equal to 1 coulomb of charge per second. Okay, so if I have 10 amps, then I have 10 coulombs of charge per second. If I have 3 amps, 3 coulombs of charge per second. Okay, and so this right here is going to be important for these stoichiometric problems. Okay, so let's go ahead and look at this. It says, what is the mass, or what mass of copper is plated out when a current of 10 amps is passed for 30 minutes through a solution containing copper 2+. Okay, so basically I'm wanting to know how much copper I'm going to put back into the zero oxidation state when I pass 10 amps for 30 minutes through this solution of copper 2+ ion. Okay, so a couple things we need to know. First of all, obviously we need to know our amperage, okay, and obviously it's connected to the coulombs of charge per second. We also need to know how long we're going to be doing this, okay, and running this current, okay. We also need to think about the number of electrons that need to be transferred into the copper 2+ ion in order to get the solidification, or the copper zero oxidation state solid to be produced. Okay, so how are we going to do this? Basically, let's start with what we're given. Okay, so we're given a time component. We were also given 10 amps. So remember, an amp is equal to a coulomb of charge per second. So if I have 10 amps, I have 10 coulombs per second, okay, as you see written here. Okay, and obviously we need to get our units to match. with respect to, our coulombs and our seconds as well. So first things first is the first multiplication we're going to carry through is to get rid of these minutes. Okay, so there's 60 seconds in a minute, so we've used that conversion factor. Okay, we also need to figure out the relationship between our coulombs and moles of electrons. Okay, so the conversion factor here, there's 96,500 coulombs of charge per mole of electrons. That's how much how much charge a mole of electron carries. Okay, so we have this conversion factor, and that's going to allow us to obviously get out of coulombs. Okay, so notice we've canceled minutes, canceled seconds. At the moment, we've canceled coulombs. Okay, so now at this point, we're in moles of electrons. Okay, so now that we're in moles of electrons, we can subsequently use the moles of electrons and the moles of copper produced to figure out how many moles of copper we've created. So, okay, this relationship here, moles of electrons cancel. Okay, and obviously if we want to get our mass, we need to take the molar mass of copper. We're going to multiply that. Okay, and we end up with 5.93 grams of copper that get plated when we pass this current through a copper 2+ solution for 30 minutes. Now, if we change the amperage, if we change the time, obviously we'd have a different quantity of copper being plated out. Okay, so let's do another problem. Okay, so how long must a current of 5 amps be applied to a solution of Ag plus 2 to produce 10.5 grams of silver metal? Okay, so basically we're just doing the reverse process of what we just looked at. Okay, so in this process, Ag plus, to bring it to Ag oxidation state 0, or Ag solid, we need to reduce it down with 1 electron. Okay, so this will allow us to get some of our conversion factors. So what are we going to do? First of all, we're going to start with our quantity of the silver metal that we want to produce. Okay, we're going to convert into moles of Ag using our molar mass. Okay, we're then going to use the mole ratio between the electrons and our plated solid. Okay, so that relationship there, that's going to allow us to go from moles of Ag into moles of electrons. Okay, then we're going to use our relationship between coulombs and 1 mole of electrons. Our moles of electrons and moles of electrons are going to end up canceling. Okay, and then we're going to use our amperage to get rid of coulombs and to get our time. So our coulombs and coulombs cancel. Notice I have seconds left over. Okay, so basically 1,878 seconds, which is basically 31.3 minutes. So it would take 31.3 minutes to plate 10.5 grams of silver metal onto this surface. So basically, we need to have our two main things, is the moles of electrons per moles of substance that we're wanting to plate. Okay, and we get that from the relationship we've seen here. Okay, our relationship between a mole of electrons and charge. Okay, and of course, understanding that amperage, okay, or amps, stands for coulombs per second. Okay, and if we can do all this, this is really just a kind of unique setup for stoichiometry.